This week's math prepare content is a bit different in that it depends on materials from this course. And that's because the lecture on mixture models depend a lot on the generative model material, which are still quite new to a lot of us. And in particular, the term learning and inference are used to mean specific tasks, and you may or may not already be familiar with what those terms mean. So if you're still not familiar, it certainly took me a while to understand what these terms mean. So let's review generative models and these terms. So in a generative model, we are modeling the joint distribution of our observed data, our training set. This is different from discriminative classifiers, which we talked about earlier on in the course, which models this distribution directly. So you might actually get a distribution for this quantity that describes this quantity maybe directly as an output of a neural network. So in a generative model, we're going to make some distributional assumptions about probability over the t's, maybe a categorical distribution, and also probability of x given t. Maybe this is a Gaussian. Maybe we use the naive Bayes assumption, so on. And what we want to do is find parameters of those distributions that make the distribution match our data. So a lot to unpack there. First, this theta here, don't think of this theta as a number or even as a vector. Think of this theta as a shorthand, a representation of all of the parameters that we need to fit. The other thing is, well, what is this? What's going on here? So this here is looking at what is the probability that we observe our data given given our theta. Right? So this is a measure of fit of our data to the parameters, and I wrote this semicolon here. This semicolon is another way of describing dependence, where we're saying that, hey, the parameters that are used in this distribution is this theta. So we are using some assumptions here. We do have the IID assumption, which lets us expand this product across all of our data points, and each of our data point is using the same distribution here. So we want our parameter to fit our data well, which means that we want this quantity, which is called likelihood, we want this likelihood to be high. We want to find theta that maximizes our likelihood. So before we get into learning and inference, let's just take a look at this joint distribution, because the way we're writing down this joint distribution is suggestive of how we're modeling the process by which the data is generated. So first we have this term right here, which suggests, hey, we're going to sample t from its distribution probability over t. And then we have the second term over here, which basically says, well, now that I have this t, I'm going to sample my x from this distribution probability of x given t, which is going to be different depending on the value of t. So let's talk about learning and inference. We've talked actually a bit about learning already. Learning means finding the values of our parameters, for example, by optimizing, maximizing the likelihood. Could be by maximizing something else as well. But the point is we're finding the values of these parameters. So in naive Bayes, it means finding these parameters, so the pi's, these are the parameters to this categorical distribution, and the theta jc's, which were these Bernoulli parameters of a bunch of Bernoullis. And in a Gaussian discriminant analysis model, our parameters are different because the form that this probability distribution takes is different, and we have some different parameters. These means and covariance matrices of our Gaussians. Now, inference means using the learned model, using the theta that we chose to make predictions for some new x. So we will do this by using the Bayes rule, right? So we have this quantity and this quantity from the previous slide. That's the joint distribution, but I also have my marginal distribution, which I can either compute or ignore if all I'm doing is making predictions. I don't care about the actual probabilities. So in a naive Bayes model, computing, well, this term right here is, we split it up like this, right? I'll use j equals 1 to d. And in a Gaussian discriminant analysis model, this probability is some normal distribution. You can write down the normal PDF as well. Some mean and right, k equals t and sigma k equals t as well. So these are values that we can compute, right? These are actually going to be either the theta jc's or 1 minus theta jc's, depending on the value of each xj. So during inference, when we have a particular x, this value right here is just a number. And then this value right here is also just a number, just a pi k. So this right here, this probability, we can actually compute. Likewise, in a Gaussian discriminant analysis model, this right here is just a particular number because we have a particular x here. We know what the mu k's are. We know what the sigma k's are. So we're going to be able to find that particular number.